Around 2,400,000,000 years ago, a chemical signal disappears from the rocks. It is a pattern in sulfur, and it can form only while an atmosphere contains almost no oxygen. For geologists, that absence is an alarm. It says that something had begun to change in the sky, above an Earth whose original atmosphere had long vanished. The evidence is scattered through black shales, iron-rich sediments, ancient soils, and minerals that still preserve the chemistry of water and air. None of these rocks is a bottle of ancient air. Together, however, they record oxygen being made, consumed by oceans and rocks, and slowly able to remain. The transition is called the Great Oxidation Event. It was not a single morning when Earth filled with oxygen, but a long, uneven planetary transformation. To reconstruct it, scientists read tiny chemical traces, then ask a question with enormous consequences. When did oxygen become a lasting part of Earth's atmosphere? Instead, oxygen appeared in pulses, reacted with rocks and oceans, disappeared again, and slowly claimed more of the planet's surface. To see that process, imagine a young Earth under a dimmer sun, with volcanic gases rising through skies unlike the blue world above us. The oceans were rich in dissolved iron, while sulfur moved between atmosphere, seawater, and seafloor, changing form whenever chemistry allowed. There was no clean boundary between air and ocean. Each exchanged chemicals continuously, making the planet one immense reactive experiment. Life, too, was already altering the atmosphere, though not through forests or animals, but through microscopic communities hidden in shallow water. Some microbes learned to use sunlight with extraordinary efficiency, splitting water and releasing oxygen as a byproduct of their patient metabolism. At first, nearly every oxygen molecule met something ready to consume it: iron, sulfur, minerals, or volcanic gases rising from below. So oxygen did not accumulate freely. It left fingerprints, oxidizing iron in seawater and transforming minerals that would later become geological evidence. The most surprising clues come from sulfur, whose atoms can preserve the signature of reactions caused by sunlight in the upper atmosphere. Those reactions leave isotope patterns that ordinary chemistry cannot easily explain, revealing whether oxygen and ozone once shielded the sky. But no single rock tells the entire story, because landscapes shift, oceans circulate, and local conditions can imitate a global change. Scientists therefore compare many fragments, asking whether the same chemical transition appears in distant basins, separated by vanished continents and ancient seas. They grind tiny samples, measure their isotopes, date surrounding minerals, and test each result against what Earth's chemistry could actually permit. Piece by piece, the old planet becomes legible, not as a photograph, but as a sequence of reactions preserved in stone. The evidence suggests a threshold was crossed, yet the crossing unfolded over immense spans of time, with reversals and regional differences. For countless generations, oxygen may have been produced and consumed without changing the atmosphere above the whole planet in any lasting way. Then the balance shifted, and a gas once trapped in chemical reactions began to remain, spread, and reshape the surface. That was the real day. The air turned blue. Not one sunrise, but a planetary transition assembled from innumerable quiet changes. And the rocks still hold its earliest clues, inviting us to follow oxygen from hidden traces toward a world capable of breathing. Before oxygen transformed the planet, Earth's air was a thin chemical veil, shaped by volcanoes, sunlight, oceans, and relentless exchange between them. To picture that world, imagine a young planet cooling beneath a hazy sky, its crust newly hardened, while molten regions still glowed beneath the surface. The atmosphere held abundant nitrogen and carbon dioxide, with water vapor, hydrogen, methane, and sulfur gases appearing in changing amounts around volcanic vents. There was no lasting blue canopy of protective ozone, so ultraviolet light reached the surface with an intensity modern ecosystems could scarcely endure. At the shoreline, rain and seawater absorbed volcanic chemicals, turning every basin into a vast reactive laboratory without walls, instruments, or observers. Volcanic eruptions supplied carbon dioxide and water, but also hydrogen sulfide and sulfur dioxide, gases that could radically alter nearby water chemistry. Their effects depended on temperature, pressure, rock composition, and distance, creating sharp chemical contrasts between a steaming vent and the surrounding ocean. Near the seafloor, hot fluids rose through fractured stone, carrying dissolved metals that met cold seawater and began building strange mineral deposits. Iron was especially important because oxygen-poor waters could hold large amounts of dissolved iron, invisible until chemistry forced it into solid minerals. These minerals settled as dark layers, quietly recording which parts of the ancient ocean remained chemically reduced and which had begun changing. Sulfur followed another path, moving between volcanic gases, seawater, sediments, and living cells in forms whose stability depended on the surrounding chemistry. Where oxygen was scarce, sulfur could persist as sulfide, combine with iron, or become buried inside minerals that resisted later disturbance. That partnership between sulfur and iron created pyrite, a brassy mineral whose tiny grains can still reveal the conditions of vanished seas. Yet the early ocean was not uniformly hostile. Sheltered shallows, mineral-rich vents, and sunlit margins offered radically different chemical opportunities for simple life. Some microbes could feed on hydrogen or sulfur compounds, drawing energy from reactions that modern animals would never recognize as nourishment. Others may have used carbon dioxide as a raw material, building organic matter without relying on oxygen-dependent respiration or a familiar food chain. In this world, survival meant exploiting narrow chemical gradients, the invisible boundaries where one substance could react with another and release energy. But the atmosphere above those waters was equally demanding, because ultraviolet radiation broke molecules apart and reshaped gases before they ever reached the sea. High in the air, sunlight drove reactions that linked sulfur atoms into new compounds, while the absence of oxygen allowed unusual products to survive. Those airborne products eventually fell with dust and rain, carrying an atmospheric signature into sediments that accumulated far below the waves. Meanwhile, every fresh lava flow exposed new rock, and every weathering front consumed gases, making Earth's surface a restless chemical balance. Nothing stayed isolated for long. The atmosphere exchanged materials with oceans, oceans with sediments, and sediments with the deep interior through burial and heat. That circulation kept oxygen scarce because any newly produced molecule encountered abundant iron, sulfur, hydrogen, or volcanic gases ready to consume it. The planet therefore looked stable from space, yet its surface chemistry was constantly shifting, preparing a conflict between production and consumption. To understand how breathable air eventually emerged, we must first enter this oxygen-starved world, where iron and sulfur ruled the limits of life. Sulfur now enters our story not as a smell, but as a family of atoms carrying different weights, and therefore different histories. Every sulfur atom has 16 protons, yet its nucleus may contain more neutrons, creating forms called isotopes that behave almost alike chemically. The lightest common form dominates nature, while heavier forms are rarer. All can enter minerals, gases, oceans, and living cells. When sulfur moves through a reaction, bonds break and reform, and isotopes may be sorted slightly, because lighter atoms usually move more readily. That tiny preference is called fractionation. A chemical process leaves one material subtly enriched, while another carries the isotopic remainder away. In ordinary reactions, the shift follows mass. The heavier the isotope, the smaller its change in speed, bond strength, or reaction rate. This creates a predictable pattern, like a musical interval repeated at different scales, linking the behavior of sulfur's isotopes through chemistry. But ancient sunlight introduced a stranger possibility, one that did not obey the neat arithmetic expected from mass alone at all. High above the early Earth, ultraviolet rays struck sulfur gases, splitting molecules and launching reactions unlike those occurring in ordinary liquid water. Because the atmosphere lacked abundant oxygen and ozone, those rays reached gases that modern air would shield from such intense exposure. The resulting products could separate sulfur isotopes in a pattern that mass alone could not explain, leaving an unexpected chemical fingerprint. Scientists call this mass-independent fractionation because the isotope differences refuse to line up along the usual mass-dependent curve for ordinary reactions. The phrase sounds abstract, but its meaning is physical. Sunlight had written a pattern into sulfur before oxygen transformed the atmosphere. Imagine three siblings leaving a house. Normal chemistry sends them outward in orderly spacing, while ultraviolet sulfur chemistry scatters them by a different rule. That irregular spacing survives when sulfur compounds settle into dust, dissolve in rain, or quietly become minerals beneath ancient seas. The atmosphere therefore becomes more than a mixture of gases. It becomes a chemical laboratory, exposing which reactions were possible at above the oceans. If oxygen had been plentiful, ozone would have absorbed much of the ultraviolet light, closing the pathway that created this anomaly. Its presence in ancient minerals thus points backward, toward an atmosphere transparent to energetic sunlight and poor in free oxygen. The clue is powerful because it records atmospheric conditions indirectly, through chemistry, rather than preserving a fragile bubble of ancient air. Yet the signal is not a single number. Researchers compare several sulfur isotopes to distinguish ordinary fractionation from the unusual pattern. They measure tiny differences in rocks, then ask whether those differences fit biological activity, volcanic gases, water chemistry, or sunlight-driven reactions. The answer emerges through combinations. Sulfur may be moved by microbes, buried in sediments, or carried across continents as atmospheric particles. Each journey can modify the signal, but the mass-independent pattern remains a recognizable echo of the sky that first produced it. In this way, sulfur becomes an atmospheric witness, preserving evidence that the young planet's air was chemically unlike our own. To read that witness, geologists must find the right minerals in ancient settings, where sulfur's hidden signature escaped burial and remained legible. The search now leaves the laboratory and enters ancient sedimentary basins, where quiet layers captured exchanges between atmosphere, ocean, microbes, and minerals. A basin is not merely a hole in the ground. It is a chemical archive, accumulating mud, salts, ash, and altered grains through time. Geologists begin by tracing rock units across hillsides, matching colors, textures, and contacts to reconstruct vanished shorelines, shelves, lagoons, and deeper water. The oldest clues often appear as dark shales, compressed blankets of fine sediment that settled slowly beneath oxygen-poor waters and sealed organic matter inside. Their black color can reflect preserved carbon, but it may also signal iron sulfides formed when microbes processed sulfur without using free oxygen. One mineral matters especially: pyrite, the brassy iron sulfide commonly called fool's gold, though here its glitter records ancient chemistry rather than wealth. When pyrite crystals grew inside mud, they incorporated sulfur from seawater, volcanic emissions, and microbial reactions, preserving several pathways in one tiny grain. A hand specimen can therefore become a meeting point between worlds: atmosphere above, ocean below, and microscopic metabolism working within the sediment. To interpret it, researchers examine crystal shapes, grain boundaries, and neighboring minerals, asking which formed first and which arrived after burial. That sequence matters because a mineral may preserve the water it touched, while another records the fluids that moved through rock millions of years later. Sulfate minerals offer a different perspective, forming when sulfur meets abundant oxygen or when evaporating waters concentrate dissolved compounds at the basin's margins. Gypsum and anhydrite can crystallize from brines, locking chemical information into pale evaporites that once occupied sunlit flats beside shrinking inland seas. Those salts are not passive leftovers. Their composition reflects evaporation, freshwater supply, circulation, temperature, and the gases dissolved before crystals began forming. In other layers, sulfate is reduced by microbes. returning sulfur to sulfide and linking ocean chemistry to the availability of electron acceptors. Shales preserve the aftermath of that reaction: pyrite, organic carbon, trace metals, and isotopes gathered together beneath an ancient water column. The surrounding basin tells scientists whether those signals formed offshore, in a restricted lagoon, near a river mouth, or within a deep anoxic pool. Each setting changes the meaning, because open water dilutes chemicals while isolated basins amplify them, turning local conditions into unusually visible geological fingerprints. Field teams test these interpretations against sedimentary structures: ripples, mud cracks, graded beds, and evaporite textures that reveal water depth and exposure. A ripple frozen in stone can indicate moving water. A mud crack can mark temporary emergence. A salt crystal can announce intense evaporation. Together, such details locate the chemistry in space, preventing a single unusual sample from being mistaken for a planet-wide atmospheric change. The strongest record emerges when independent clues agree: sulfur isotopes in pyrite, sulfate abundance, iron minerals, carbon burial, and basin architecture. Space is alone, and every mineral can be overprinted by heat, pressure, groundwater, or later fluids that rewrite its original message. That is why geologists compare fresh interiors with weathered surfaces, analyze several grains, and repeat measurements across layers separated by distance and age. Slowly, scattered observations become a basin-scale story, showing how gases entered water, how reactions moved through sediment, and where oxygen could survive. And when the same sulfur anomaly fades from younger rocks, the change becomes impossible to ignore. The atmosphere itself has altered the pathway. In younger rocks, the strange sulfur imbalance is no longer scattered through minerals. It has largely vanished, leaving a silent boundary in Earth's chemical record. That disappearance is not a missing clue, but the clue itself: something in the atmosphere began blocking the reactions that once stamped sulfur with an uneven signature. To understand why, we return to sunlight, striking volcanic gases high above a planet whose air contained almost no free oxygen. There, ultraviolet energy could split sulfur-bearing molecules, sending fragments into different chemical routes before rain and dust carried them toward the ground. Because those routes were not simple copies of one another, they enriched sulfur isotopes in patterns that ordinary mass balance could not predict. Scientists call the result mass-independent fractionation, a signal written by atmospheric photochemistry, rather than by familiar differences in reaction speed. Its survival in ancient sediments means those particles escaped, settled, and became locked inside minerals before oxygen changed the chemistry overhead. But oxygen is chemically restless, and even small amounts would attack reduced gases, redirect sulfur compounds, and reshape what ultraviolet light could reach. The first effect would occur high in the atmosphere, where oxygen reacts with methane and other gases that helped preserve a transparent ultraviolet window. As methane declined, a new molecule became possible: ozone, formed when sunlight split oxygen and free oxygen atoms recombined above the young oceans. Ozone absorbed the most energetic ultraviolet wavelengths, weakening the photochemical engine that had created sulfur anomalies in the first place. The atmosphere had not merely gained a gas, it had gained a filter, changing which reactions could begin and which products could survive. That filter explains the geological pattern. Younger sulfur minerals still contain ordinary isotope differences, but the unmistakable mass-independent excesses are missing. In other words, sulfur continued cycling through oceans, sediments, and volcanoes, yet the atmosphere stopped adding its earlier photochemical accent. This distinction matters because ordinary fractionation can arise in many environments, while mass-independent fractionation requires a particular architecture in the air. When that architecture disappeared, the signal disappeared with it, giving geologists a chemical marker for the atmosphere's transition rather than a local sedimentary accident. Yet the boundary is rarely a razor line, because oxygen was produced unevenly, consumed by rocks, and mixed through an atmosphere in motion. Some basins lost the anomaly earlier than others, reflecting local burial, volcanic emissions, ocean circulation, and the uneven spread of oxygenated conditions. That regional complexity makes the record more valuable, not less, because it reveals oxygen as a spreading environmental force rather than an instant switch. Researchers therefore compare sulfur from different minerals, ages, and settings, asking whether the same disappearance appears across independent pieces of the ancient landscape. They also examine sulfate and sulfide together because their relationship records whether sulfur was exposed to oxygen before entering sediments or remained chemically reduced. When the anomaly fades while other chemical changes emerge, the simplest explanation is a new atmosphere governing an old planetary cycle. The missing sulfur signal therefore marks more than absence. It marks the arrival of a protective ozone layer and a fundamentally different sky. By the time this pattern becomes normal, oxygen is no longer only a fragile byproduct, it is beginning to reshape Earth's surface chemistry. The vanished anomaly points forward toward microbes producing oxygen, minerals rusting, oceans reorganizing, and a planet steadily learning how to breathe. Before oxygen transformed the atmosphere, its first makers lived as thin, almost invisible communities along sunlit shores, where sunlight met ancient seawater. They were cyanobacteria, descendants of a microbial experiment, that learned to use water as an abundant electron donor during photosynthesis. That innovation carried a hidden consequence. Splitting water released molecular oxygen, a reactive waste product that slowly escaped from each microscopic cell. At first, this output was not a breath of fresh air, but a chemical challenge entering a world built without free oxygen. The young planet offered countless substances ready to react, and oxygen rarely survived long enough to drift upward into the atmosphere. Its earliest barriers waited in the ocean, beginning with dissolved iron carried upward from deep water and hydrothermal systems beneath the seafloor. When oxygen met that reduced iron, the two combined, forming iron oxides that settled as rust-colored particles across the seafloor. Layer after layer, these reactions pulled oxygen back into minerals, preserving the encounter inside rocks rather than allowing it to accumulate overhead. Iron was only one sink. Sulfur compounds, especially those containing reduced sulfur, also consumed oxygen through reactions at sediments and ocean margins. Volcanic gases added another demand, releasing hydrogen sulfide, methane, and other reduced molecules that oxygen would relentlessly oxidize before reaching the sky. Every new molecule of oxygen entered a chemical battlefield, meeting iron, sulfur, and volcanic gases faster than winds could distribute it. For immense stretches of time, production and consumption balanced one another, leaving the atmosphere nearly oxygenless despite flourishing photosynthetic activity. Yet cyanobacteria kept working, multiplying in mats that trapped sediment, stabilized shorelines, and formed layered structures later preserved as stromatolites. Their world was microscopic, but its chemistry reached across entire basins because each mat connected sunlight, water, minerals, and atmosphere. Inside these communities, cells captured sunlight with pigments, built organic matter from carbon dioxide, and released oxygen into surrounding films of water. Some oxygen reacted immediately nearby. Some traveled through pores and currents, searching for reduced chemicals still abundant in the ancient environment. The balance could vary from one shoreline to another, making oxygen a local disturbance long before it became a planetary signal. Near iron-rich waters, it vanished into minerals. Near sulfur-rich sediments, it helped produce oxidized compounds that changed the chemistry of burial. Near volcanic vents, fresh gases continually replenished the planet's chemical appetite, drawing down oxygen as quickly as biology supplied it. This is why oxygen's first appearance should not be imagined as a sudden blue sky, but as countless invisible contests repeating everywhere. Over generations, however, the producers altered their surroundings, and every reaction that consumed oxygen became part of a finite geological inventory. As accessible reduced iron and sulfur became buried or transformed, some oxygen began surviving longer, lingering in water before escaping toward the air. The atmosphere had not crossed its great threshold yet, but the direction of change was becoming harder for geology to erase. Cyanobacteria had turned sunlight into a persistent planetary force, even while rocks and gases struggled to absorb its consequences everywhere. What began as microbial metabolism was preparing a surface revolution, but oxygen first had to survive the chemical sinks of oceans, rocks, and sky. Once oxygen began escaping its microscopic factories, the decisive question changed. What could stop the planet from swallowing it again? At first, every new molecule met a waiting chemical debt, hidden in minerals, seawater, volcanic gases, and the deep crust. These surface sinks did not vanish overnight. They filled gradually, like invisible reservoirs, receiving more oxygen than their reactions could permanently consume. The earliest evidence may be microscopic, as iron minerals changed color and sulfur-bearing sediments recorded a new balance between burial and exposure. Reduced iron especially acted like a sponge, binding oxygen into rust and carrying its chemical memory downward through ancient seas. But each buried layer left a little less reactive material in circulation, giving the next pulse of oxygen more room to travel. Sulfur offered another threshold, because oxygen transformed dissolved sulfide into sulfate, a form that could move widely through oceans and sediments. That conversion changed sulfur from a local poison into a mobile chemical currency, linking microbial activity with distant deposits, shorelines, and seafloor mud. Sulfate also fed new microbial reactions, allowing communities to breathe sulfur compounds and return sulfide to waters where oxygen could oxidize it again. The ocean therefore became chemically layered, with oxygenated shallows above darker, reducing depths where iron, sulfur, and carbon followed different rules. In some basins, oxygen reached the seafloor. Elsewhere, anoxic water persisted, preserving a patchwork rather than a single planetary condition. That patchwork mattered because the atmosphere could brighten while much of the ocean still held chemical traps capable of consuming oxygen. As sinks weakened, oxygen began accumulating above the waves, where sunlight split oxygen molecules and produced a fragile but protective layer of ozone. Ozone absorbed dangerous ultraviolet radiation, especially the wavelengths that once drove sulfur's strange atmospheric reactions and stamped their signatures into ancient sediments. With that shield in place, photochemistry changed again, closing pathways that had flourished only beneath an oxygen-starved sky above the young ocean. The disappearance of mass-independent sulfur signatures now made chemical sense. Ozone and oxygen had rewritten the ultraviolet laboratory above Earth's surface. Yet persistence required more than an atmospheric shield. Oxygen had to escape continuous exchange with rocks, seawater, sediments, and volcanic emissions. That escape became possible when burial outpaced recycling, carrying reduced carbon and sulfur beneath the reach of surface oxygen and sunlight. Each buried grain was small, but geological time multiplied small advantages until the atmosphere retained oxygen between pulses of volcanic and biological production. Meanwhile, sulfate-rich waters altered mineral formation, changed nutrient availability, and gave sulfur-cycling microbes new opportunities across expanding oxygenated coastal margins. The result was not clean or uniform, but a moving chemical frontier, advancing through some environments while retreating from others. Every advance altered the next reaction, so oxygen's spread became self-reinforcing wherever exposed surfaces could no longer neutralize it quickly. This was the tipping point, not oxygen's first appearance, but its growing ability to remain, circulate, and reshape the planet even when production paused. The evidence survives in iron, rust-colored soils, trace metals, and minerals whose transformations reveal oxygen moving between ocean and land. Together, these clues show a planet crossing a threshold, ready for the next question. How did oxygen transform the ocean itself? The ocean itself became the next great archive, recording oxygen not as a single event, but through iron, sulfur, and changing minerals. For most of early Earth's history, dissolved iron filled deep seawater, kept soluble by chemistry that excluded free oxygen from the environment. When oxygen entered those waters, it reacted immediately, converting invisible ferrous iron into ferric minerals that could settle onto the sea floor. Layer after layer, the precipitated iron alternated with silica, preserving a striped chemical memory known today as a banded iron formation. These formations are not photographs of ancient waves, they are reactions frozen in stone, marking where oxidized material met an iron-rich ocean. Their minerals changed as conditions evolved. Iron carbonates and silicates gave way to oxides, while the ocean gradually lost its dissolved iron. The shift was uneven, because oxygen first vanished into local chemical sinks before it could spread across entire basins and reach the atmosphere. Sulfur preserves a separate witness to that transition, especially in isotope patterns created under the light of an oxygen-poor sky. Earlier sediments carry mass-independent sulfur signatures, evidence that ultraviolet chemistry operated freely when atmospheric oxygen and ozone remained scarce above them. Later, those signatures fade, not because sulfur stopped moving, but because oxygen and ozone redirected the reactions that formed them in sunlight. That disappearance matters beside the iron record. Two independent chemical systems now point toward the same expanding presence of oxygen. On land, another clue appears in red beds, ancient river and floodplain sediments colored by iron oxides instead of remaining gray. Red beds show that oxidizing conditions reached exposed surfaces, where iron-bearing grains met air, rainwater, and sunlight before burial again. Their spread through younger continental rocks suggests oxygen was no longer trapped only in seawater. It had begun crossing the boundary onto land. Meanwhile, trace metals record the biological and chemical consequences, because oxygen changed which elements dissolved, traveled, or settled within sediments. Molybdenum, chromium, and uranium became especially informative, responding to oxidation and reduction as rivers connected weathered continents with the sea. Their concentrations cannot provide a simple oxygen meter, yet changing combinations reveal shifting pathways between atmosphere, crust, ocean, and living organisms. The mineral record grows richer, as well. Sulfides oxidize, carbonates dissolve or precipitate, and clay minerals reorganize under unfamiliar chemical conditions. Each transformation has a local story, but together they trace oxygen's expanding reach through connected reservoirs rather than a perfectly synchronized global wave. Some basins oxidized early while neighboring waters stayed anoxic, preserving iron-rich sediments and sulfur chemistry that had already vanished elsewhere. This patchwork explains why no single rock type can carry the entire history, and why scientists compare signals across continents and ages. When banded iron formations, red beds, sulfur isotopes, and trace metals agree, their combined message becomes stronger than any isolated measurement. They reveal oxygen moving in stages, first through shallow waters, then deeper basins, later soils and rivers, and finally the atmosphere itself. The evidence does not describe a clean switch from darkness to blue skies. It describes pulses, delays, reversals, and thresholds across Earth. By reading these minerals together, geologists can watch an invisible gas become a planetary force, preparing the ground for a precise timeline. Once the clues are scattered across continents and separated by immense ages, the first task is to place every fragment on one shared clock. That clock begins with isotope measurements, because atoms of the same element can preserve how chemical reactions unfolded in ancient water, air, and rock. Researchers collect powdered minerals, dissolve them carefully, and measure tiny differences in atomic mass that remain invisible to ordinary geological inspection. Those differences do not announce a date by themselves. They become meaningful only when paired with the age and setting of the material containing them. Mineral ages supply the anchors, using radioactive decay as a steady natural clock that can survive deep burial, folding, and metamorphic change. Crystals forming in ancient volcanic ash may date an eruption, while grains carried into a basin record landscapes that existed somewhere beyond the shoreline. Scientists therefore ask not only when a mineral formed, but whether it formed inside the environment whose chemistry they want to reconstruct. Sedimentary context provides that missing dimension, distinguishing a quiet seafloor from a tidal flat, evaporating lagoon, river delta, or wind-blown continental surface. Layered rocks reveal water depth, current direction, shoreline position, and exposure to air, turning isolated chemical results into evidence tied to real places. Next comes comparison. Sulfur anomalies, iron oxidation, sulfate minerals, and red beds are lined up against their host rocks and neighboring formations. A single outcrop can mislead, because local fluids, later weathering, or a vanished basin may imitate a broader atmospheric transformation. Confidence grows when independent signals shift together, especially across separate basins that once shared oceans, coastlines, or connected volcanic provinces. Yet the changes rarely align perfectly, and that imperfect overlap is valuable, revealing a transition with regional timing instead of one planetary instant. One basin may preserve waters lacking oxygen, while another, closer to exposed land, records oxidation earlier through altered minerals and rust-colored sediments. To test such differences, researchers build chemical models that simulate reactions among seawater, volcanic gases, sediments, microbes, and newly available oxygen. These models estimate how rapidly oxygen could be consumed, buried, or transported, then compare those expectations with the minerals and isotopes actually preserved. If a model requires oceans to remain reducing, yet the rocks contain oxidized iron, the mismatch exposes an assumption that needs revision. By adjusting gas fluxes, biological production, ocean circulation, and mineral burial, scientists narrow the range of histories capable of producing the observed record. The result is not a perfectly straight line, but a probability landscape, with early hints, rapid pulses, pauses, and delayed regional expansions. Some evidence suggests oxygen first accumulated in sheltered surface waters, while deeper oceans and continental interiors remained chemically resistant for much longer. Other records point toward repeated rises and retreats as volcanic activity, nutrient supply, climate, and fresh geological sinks repeatedly changed the fate of oxygen. Timeline building also depends on uncertainty, because every date carries measurement limits, erosion risks, and the possibility that later events disturbed older signals. Rather than hide those uncertainties, scientists map them openly, asking which conclusions remain secure across different samples, laboratories, and model choices. That discipline turns scattered observations into a sequence: microbial oxygen production, overwhelmed chemical sinks, persistent surface oxygen, and expanding atmospheric consequences. And once the sequence becomes visible, the Great Oxidation Event emerges not as a sudden switch, but as Earth learning to hold oxygen. Holding oxygen changed more than the atmosphere. It rewrote the planet's chemistry, opened new energy pathways, and began a biological upheaval without precedent. For billions of years, microbes had lived on narrow chemical gradients, extracting modest energy from sunlight, minerals, fermentation, or gases rising through seafloor sediments. Oxygen offered a more powerful reaction, allowing cells to draw far greater energy from the same food and reshaping which organisms could thrive. That advantage did not arrive gently. As oxygen spread through water and rock, familiar metabolisms became dangerous, and entire microbial communities faced extinction. Sulfur helps preserve that disruption because its isotopes respond to atmospheric chemistry, recording pathways that living organisms and minerals experienced long after the original reactions ended. The old mass-independent sulfur signal belonged to an oxygen-poor sky, where ultraviolet light could build unusual isotope patterns in sulfur-bearing gases. Once oxygen and ozone became persistent, those photochemical routes changed, and the anomaly faded from younger rocks, leaving a boundary between planetary states. That boundary was not a clean line everywhere. Oxygen rose unevenly, pulsing through oceans and landscapes as local sinks filled at different speeds. In shallow seas, dissolved iron captured oxygen and settled as rust-colored minerals, turning invisible chemistry into thick layers on ancient seafloors. Elsewhere, sulfate accumulated, feeding sulfur cycling and giving microbes new opportunities to trade electrons across sediments, vents, and increasingly oxygenated waters. These metabolisms multiplied the planet's chemical vocabulary. Sulfide, sulfate, iron, manganese, nitrate, and oxygen became partners in an expanding network of reactions. Every new reaction created niches, but also rivalries. Microbes competed for gradients, poisoning neighbors, bearing nutrients, and transforming habitats molecule by molecule. The upheaval extended into the continents, where oxygen attacked exposed minerals, accelerated weathering, and carried fresh chemical ingredients toward rivers, lakes, and seas. Earth's mineral inventory began to expand dramatically because oxygen allowed elements to combine in forms that earlier atmospheres could rarely sustain. Many familiar minerals today, from oxidized iron compounds to diverse sulfates, belong to this later chapter in Earth's chemical history. Mineral diversity was not merely geological decoration. It created surfaces, pores, catalysts, and nutrient stores that life could exploit in increasingly elaborate ways. With more energy available, cells could grow larger, maintain complex internal machinery, and cooperate, though the road toward complexity remained slow and uncertain. Oxygen also helped form ozone high above the surface, filtering harsh ultraviolet radiation and making exposed environments less hostile to vulnerable biological chemistry. That shield did not create complex life by itself, but it widened the stage, allowing evolution to experiment across shallows, shores, and open water. Much later, oxygen levels fluctuated again, and complex organisms remained constrained by climate, nutrients, predators, and accidents written into fragile ecological histories. Yet the inheritance was durable. An oxygenated world could support bodies, tissues, movement, and senses on scales impossible beneath the earlier chemical regime. The evidence survives in concert: rusted iron, vanished sulfur anomalies, altered trace metals, and mineral assemblages that could only form under changing redox conditions. Together, these records reveal no single instant, but a planet crossing thresholds, repeatedly absorbing oxygen until new chemistry became self-reinforcing. Sulfur isotopes therefore preserve more than an atmospheric measurement. They mark the moment Earth's old possibilities narrowed, and its future possibilities multiplied. In that silent inheritance, the air became an archive, evidence that life changed Earth, and that Earth, changed in return, made complex life possible.